formation. So as 85% of you just told me, when we have a case where delta G of formation is less than 0, what we're talking about here is a compound that is thermodynamically stable relative to its elements. So that means we know the inverse as well, which is when we're talking about a case where delta G is now greater than 0, the compound is going to be thermodynamically unstable relative to its elements. So anytime you're looking at delta G of formation, just remember to think about this is just the delta G of a reaction where you're forming a compound. So it should make sense that if it's negative, it's going to be spontaneous and you're going to have a stable compound here. So we could look at any number of examples. Really, we could pick any compound to look at. But up on the screen here, I'm just putting the compound, the formation of benzene. We've looked at benzene a lot. So benzene has a delta G of formation of 124 kilojoules per mole. Is benzene stable or unstable compared to its elements? I can't really tell the difference between stable and unstable when you say it. So everyone start at the same time. Go. Okay, excellent. Benzene is unstable compared to its elements. So that means the reverse reaction here is going to be stable. The reverse reaction is going to be spontaneous, where we actually have the decomposition of benzene. So when we're seeing this, when we're seeing that the reverse reaction is spontaneous, a question that might immediately come to us is, well, why did we just spend all this time talking about benzene? Because clearly benzene is just going to break down, right? Why do we form benzene and not have it immediately decompose into its elements? Thermodynamically, that is what should happen, and it is what does happen. But the reality is that this reaction, this decomposition of benzene, is actually very, very slow. It's so slow that we use benzene all the time in organic reactions. We don't see it break down even when we heat it up. It's because even though this is thermodynamically a non-spontaneous reaction to form benzene, it's very slow for the actual decomposition of benzene to occur. So this is just another case, and I'll keep saying this, and when Professor Drennan starts talking about kinetics, she'll keep repeating this as well. What we want to keep in mind is that delta G tells us whether a reaction will happen or whether it won't happen. It tells us absolutely nothing about how long it takes for that reaction to happen. It tells us nothing about the rate of the reaction. We'll keep seeing examples of this, so hopefully no one will be confused by the time we do get to kinetics. So if we're talking about calculating delta G for any reaction, now we actually have several ways to do it. The first way is very analogous to thinking about delta H for the reaction. We can just look up a table where we have delta G's of formation. So we can take the sum of the delta G of formation of the products and subtract from it the delta G of formation of the reactants. We also have another way, if maybe we don't have that information available to us, we can also take a look at using this reaction, or this equation right here, which is telling us that delta G of a reaction is equal to the change in enthalpy minus T delta S. So that tends to be very helpful, especially when we want to take into consideration temperature. So let's take into consideration temperature. We've done this a little bit so far, but let's really take a look at some reactions where temperature is going to make a big difference.